This lesson has been developed in the framework of SCILED project. Module 3, Footwear Design Engineering, Unit 3, Engineering Footwear for Mechanical and Hydrothermal Comfort.
Lesson 3.6. Managing Thermal Comfort. This lesson is structured as follows.
Introduction: Predicting thermal comfort in virtual prototyping stage. Footwear thermal assessment and modeling.
Introduction.
Thermal comfort of footwear consists of two aspects: thermal conductivity and vapor exchange characteristics. Depending on the external conditions, there might be heat transfer from hot external environments towards the foot, heat loss from the foot towards cold or external environments, as well as water vapor transfer from wet external environment towards the foot and moisture transfer from perspiration from the foot surface towards the microclimate of the footwear and then towards the external environment, if the characteristics of the footwear structure allows so. Thermal comfort is always location, climate and application dependent. The designer needs to determine the occupational conditions of use, if the footwear is used in an occupational context, or the weather conditions in which the footwear is to be used. Footwear products shall be designed to shield from adverse health-damaging effects, for example, block heat, block water penetration, and/or to enhance certain aspects that reduce discomfort, for example, to allow for heat exchange in hot weather conditions, to improve vapor exchange, etc. Shielding may include both the upper and sole assemblies, whereas enhancing discomfort is mainly restricted to the upper and insole parts. Matching footwear products to the requirements of use requires the selection of optimal materials with appropriate thermal conductivity and vapor exchange properties. The elimination of failure points where parts are joined together, i.e. selection of appropriate seams, stitches, adhesives and polymer properties such as TG and melting or decomposition temperatures, as well as the arrangement of parts and the 3D shaping of internal volume surface area and characteristics of the upper and sole. The presented Rispylon shoe is an example of product adapted to the requirements of use with 4-layer uppers, outer, lining, nanofiber membrane and inner material.
Predicting thermal comfort in virtual prototyping stage.
For most textile, leather and membrane components there are well-defined heat conductivity, for example ISO 5085, ISO 4880, vapor exchange, for example ISO 15496, water and air permeability tests, for example ISO 811, ISO 4920, ISO 9237 etc., and data in several material databases. Supplementary aspects such as surface wetting, water absorption, and hygroscopic endo or exothermal aspects need to be taken into account, thus making footwear material selection for engineering thermal performance a very complex issue, with any improvement limited to marginal effects rather than full breakthrough solution to the problem. For any real prototypes, the testing of above-mentioned requirements could be performed concerning upper and lining assemblies, for example ISO 17699 and ISO 17705, or whole footwear product, for example ISO 20877. Although understanding and managing performance at component level, fabric, leather part, membrane, plastic sheets etc., is important, investigating the performance of whole footwear is far more than summing up the performance of individual parts. This is due to the combined effects of assemblies of different parts, the joining options used, the characteristics of folds and seams and other parameters. With regard to virtual prototyping, managing thermal characteristics is possible today using computational simulation tools like finite volume method for analysis of heat transfer through footwear between the shoe's user and his surroundings, finite element analysis to simulate the measured temperature distributions inside footwear and provide recommendations to aid the design of comfortable footwear in temperate conditions, computational fluid dynamics techniques to simulate a three-dimensional steady-state turbulent flow and heat transfer in the model. The virtual solutions are based on whole footwear thermal assessment models that fall into two categories: thermoregulatory models and thermal models, Alemani et al., 2013.
Footwear thermal assessment and modeling.
Most thermoregulatory models are based on the well-known Latins human body model that has been used extensively for clothing studies. Some of them are very simple and passive, incorporating thermal and geometrical properties of body tissues in discrete voxels and utilizing finite element analysis techniques for simulation.
There are also cybernetic predictive models for thermoregulatory response, vasoconstriction or vasodilatation, sweating, shivering, considering the thermal state of the body, core temperature, skin temperature, heat flows and other conditions. Most thermoregulatory models can predict heat flow in different states of motion and environmental conditions, but there is very limited number of available tools for evaluating perspiration and vapor phenomena. In addition, it is generally agreed that more work is needed for improving correlation with laboratory results and validating the tools.
The most completed footwear model presented in the literature incorporates aspects of the Latins clothing model and predicts the thermal and water vapor resistances over several footwear sectors from the properties of its components. The footwear is simplified to a cylinder with heat and humidity losses in a radial direction only. Puskers et al. 2019, developed 3D simplified thermal models, figure, of shoes based on geometry obtained from images of real prototype in order to determine the temperature of the outer surface of selected parts of the shoes, sole and uppers, for 4 different ambient temperatures, a -10 degrees Celsius, B 0 degrees Celsius, C 10 degrees Celsius, D 20 degrees Celsius. Basic shoe geometry and physical thermal parameters of materials was kept. Cobble et al. 2011, simulated in shoe temperatures in various locations using numerical thermal models based on simplified and modified 2D and 3D models. The thermal material properties of the upper shoe, sole, and air were considered. Figure present the simulated foot temperatures, A, foot heat flux vectors, B, foot heat flux magnitudes, C, shoe temperatures, D, shoe heat flux vectors, E, and shoe heat flux magnitudes, F.